Živijo, pozdravljeni vsi, dobrodošli na januarskem večeri na observatoriju. Srečno novo leto tudi vsem, letos se prav prvič se dobimo tukaj. In danes se za nas pripravlja predavanje Aniša, predavanje bo v angleščini. Aniša je naša sodelavka na fakulteti za matematiko in fiziko, dela kot postdoc. In se, ko pravite, dela tudi sodeluje v skupini z Marušo Bradač in dela z teleskopom, James Webb teleskopom. Tako da po samem predavanju, ki traja okoli 45 minut, so na vrsti vprašanja z vaše strani. Če bo potrebno, bom jaz seveda poskusil kaj prevajati, če niste preveč prepričani svojo angleščino in obratno. To velja tudi za tiste, ki ste na Zoomu, ki imate opcijo vprašati Q&A, lahko to postavite svoje vprašanje. Tako da lepo predavanje želim. Aniša.
Great. Thank you, Samuel. Hi everyone, my name is Anishya Harshan. I guess Samuel already introduced me, but I'm a postdoc at the Faculty of Mathematics and Physics at the University of Ljubljana. And today I'll tell you about a little bit about the unexpected news that we have received from this space telescope called the James Webb Space Telescope about the very early universe, which is what I and our team work on. Let me start by giving you a little bit of an introduction about what the James Webb Space Telescope is. So it's a really large telescope which is in the space, which is kind of evident from what it's named. It's one of the largest telescopes that we have right now in space. And you can see how big it is by looking at how tiny people are looking in front of the large telescope. The telescope's mirror is about 21 feet in diameter, which is what is shown in this golden color. So and it's been like 3 years since its launch. It was launched on Christmas Eve in 2021, when I was still a PhD student, and I was looking at JWST being launched as I was writing my thesis, which was fantastic for me personally, but also for humanity. It was like the biggest Christmas gift for humanity that astronomers have ever provided. So it's also at the farthest telescope that we have put from Earth. A little bit of a schematic here. So our Earth is there. The predecessor of the James Webb Space Telescope, no problem. The predecessor of the James Webb Space Telescope was called the Hubble Space Telescope. It's actually just within 600 kilometers from the surface of our planet. The moon is about 400,000 kilometers from our planet, whereas James Webb Space Telescope is almost 1.5 million kilometers away from the planet. So it is almost 4 to 5 times farther away from the moon from Earth. So this is truly one of the most biggest engineering marvel that our humanity has ever created, right? So this alone is so crazy to me. To start a little, now this is an extremely costly experiment, one of the costliest experiments that humanity has ever created. So we need to understand why do we need this particular telescope and this bigger telescope and this costlier telescope. It has required a lot of our resources. To do that, we will kind of look into what the telescope actually does. Okay, let me try to take this away. So for that, we need to understand what the telescope is doing. You can think of the telescope as a really big camera. So what does a camera like our phone does? It takes the images of things using light. Now, what is light? It is what we call light is a small part of a spectrum of something called the electromagnetic radiation. It is everything that is coming from outside our planet, from our the light that is coming from the projector, all of this is electromagnetic radiation. Even the light that is coming from the sun, the stars, everything else is electromagnetic radiation. And all of that light can be split into different things, something that we call wavelengths. So this light can be split into wavelength, which is what we show here. Now, when you look at this, what do you remember? Does anybody want to guess? What are you familiar with this image? Yeah. Okay, so well, since we have slightly more, this is actually the album cover of Pink Floyd, but that is not what we're going to be looking at. For the younger audience, maybe you guys don't know, which is kind of sad, but that's okay. So what I'm showing here is a singular ray of light that goes through a glass prism. It splits into the constituent wavelengths, which is visible for us with our naked eye. So light or visible light is simply the part of this electromagnetic radiation that our eyes can perceive. But light is not only what we can perceive. There are other wavelengths. So all of these different colors can be classified into different wavelengths. So we can classify electromagnetic radiation into different wavelengths. So light, however, is not only the visible spectrum. It is much more beyond and after the wavelengths of the visible spectrum. Visible spectrum is simply what we can see with our eyes. So as I said, the sun, for example, is producing wavelengths or electromagnetic radiation across this wavelength regime. So on the horizontal axis, you can think of as wavelength. So there are we have divided electromagnetic radiation into different wavelength regimes. We call them gamma rays, X-rays, ultraviolet rays, visible light, which is in the color that you see. Then there is the infrared spectrum, which is around here. Then you have all of the radio wavelengths. And now the brown things that you're seeing is how much the light that is coming from space is actually able to reach our planet. So you can think of that if it's completely brown like it is here, none of the light that is in this wavelength that is coming from the space is actually able to transmit through the atmosphere to our planet. So on Earth, we cannot see this wavelength regime, right? Which is really good for us as humans, because that is how we are able to survive. Because as you can see, this is where UV radiations is, and we know that if our atmosphere does not block out the UV radiation, we get a lot of diseases, like poor people in Australia who have a big hole in the atmosphere, and UV light passes through there, and there is a much more higher incidence of things like skin cancer. Thankfully for us in Slovenia here, that is not so much a problem. But still, that hole that has appeared is because of human activities and so on. But what we can see that our atmosphere is there, and it is protecting us from from all of the unwanted radiations that we are seeing. So you can now also see in the visible spectrum here that it is completely reaching our planet on the surface, which is why all of the light that is coming from the sun or any of the astronomical objects, which is in this spectrum, we are able to see. And that is exactly how we are able to see sunlight or moonlight or any of the stars. After that, we have this giant trough of place where we cannot again see any of the light that is coming. This spectrum is called the infrared radiation. And then again in radio, some part of the radio spectrum, we are actually able to transmit it onto the Earth. And this is how all of our devices actually work. All of our laptops, internet, phones, all depend on the radio wavelength, radio communication, which depend on this the fact that we are able to transmit across the planet on the Earth. So if we want to see the light, study the light that is coming either invisible or in radio, it is possible to do that from on the surface of our planet. And that is why we have large telescopes that are based in radio. And also we have many telescopes that actually see the visible light, much like our Golovcu observatory, which is a smaller telescope, but there are really, really large telescopes, much like that work very similarly to the Golovcu observatory, that is able to study light that is coming in the visible spectrum. However, as you can see, this part or this part or that part, you need to be in the space to be able to study that light. And that is exactly where our space telescopes, much like the Hubble telescope as well as the James Webb Space Telescopes, come in. So before you saw that, now that same spectrum is kind of split again here, which is shown in the, so you can see the UV light in purples, the visible light that we see from our eyes in Vidgyor, and all of the infrared light here in red colors. So Hubble Space Telescope, which has been working for a couple of decades now, mainly sees light that is in ultraviolet, as well as most of the visible spectrum and a very tiny bit of the infrared spectrum. There is another space telescope called the Spitzer Space Telescope, which is not as huge as the Hubble or the James Webb Space Telescope, can actually see light that is in the far infrared. So the longer wavelengths of the infrared spectrum, we call the far infrared spectrum. That Spitzer telescope has been able to see, and we have a lot of work that is done, studies that is done using that telescope. So you can see that this range of wavelength was completely invisible to us before the James Webb Space Telescope. And that is exactly why we need something like the James Webb Space Telescope to be able to see light that is study the light that is coming from the space across the wavelengths. Now, you might think that's a very small little part of the wavelength. Why do you need to see that to be able to study galaxies and stars or other things that we study? You can think of it this way. If you are colorblind and you cannot really distinguish between green and purple or green and red, so red and green kind of appears the same to you because you do not have the ability to see either green or red, then both of them look the same. And you go to the supermarket and you want to buy green grapes, but then you come home with red grapes and your family is angry with you because you brought the wrong grapes. So although you can kind of understand that a grape is a grape, but the properties of grapes is not visible to you because you cannot detect that particular color in the wavelength. So, which is why we, as astronomers, we require a multi-wavelength imaging or multi-wavelength studies of all of these astronomical objects to be able to completely understand what's going on in those astronomical objects and to study where they come from. So that is kind of why James Webb Space Telescope was made, to make us this blind spot that we had, to fill that blind spot. So James Webb Space Telescope, as I said, was launched in 2021 Christmas Eve, but it took about 6 months for all of the for it to reach, first of all, the Lagrange 2 point, which is where it's based, and which is, as I said before, almost 1.5 million kilometers away from the planet. And a lot of calibrations had to be done of the mirrors and the instruments that are there on the telescope, and all of the data had to be collected. The first data had to be collected. All of that data had to be reduced to make pretty images like the one that you see over here. And the first image from JWST was given to us on July 2022. So it's been almost 2.5 years of the first image of JWST. There were a few other images, but this image is the first deepest image of the universe that we have in the IR wavelengths that I talked about a little bit before. So this image itself was actually studied, or rather observed, by the Hubble Space Telescope. And what we see on the right side is the view of this same field with the Hubble Space Telescope. And this is from the James Webb Space Telescope. And you can see a vast difference between the two images, right? So not only is this image much more sharper and much more sensitive, which Hubble was not able to produce because Hubble is not as big as James Webb Space Telescope. JWST is almost 3 times as bigger as HST, which is why it is able to see, which is extremely small objects that you can see, which are all of these little specks that you see that you cannot see on that image. They're all little galaxies, which are really small and they're really far away from us, which were completely not visible in the HST image. Not only that, even the ones that were visible, you can see we are able to see much more detail in the JWST images, which was not available with the HST images. Also, the colors, although these are false colors, so which by that we mean that we just get 3 images in different wavelengths and we give them red, blue, and green colors and we create these images. But this, although the colors may look the same, the actual wavelength of these images are completely different. So you are getting brand new information of things that you did not even know existed with the JWST. So now I think we've established that JWST is pretty fantastic, and we've been able to do a lot since the July 2022 first image that was given to us. And you may have, and JWST does not shy away from making a lot of headlines. We have at this point seen lots of news articles from JWST, which shows the first most detailed photo of the ancient distance galaxies, which I showed earlier. We saw that with JWST, people were finding really massive galaxies, which initially people thought that should not exist. Then there were sparkler galaxies, which were the tiniest, most farthest away star clusters and so on, and there were other early galaxies which were kind of they were like challenging the model of the universe that we had before we launched JWST. And there were many headlines that were made that were about asking if JWST observations is breaking the cosmology of the universe, the model of the universe that we had created prior to JWST. And if there was even if Big Bang didn't happen or not. So there was a lot of noise that JWST made. So in this talk, I'll tell you a little bit about a few of those really unexpected results that we got from JWST and what that means for astronomy as we go forward. So before that, let me give you a small history of the universe itself. Because we are going to look at the very early part of the universe, this is kind of important. So here is the fairly used Cosmos a calendar from the show called Cosmos. I don't know if you are familiar with this show. Here, they have created the history of the universe, the entire history of the universe, which is about 13.8 billion years long. They have compressed all of that into one calendar year. And what that would mean is that first day of midnight, so New Year's time, is the Big Bang. And towards as you go to December, New Year's Eve, next year's New Year's Eve is present day time. So if we do this after Big Bang, which was January 1st, 0000, the first galaxies actually start to appear, first stars and galaxies start to appear around the first week of February. Around March, you start getting our Milky Way style galaxies, which you can see over here, this giant spiral over here, which is kind of what our galaxy looks like. And around August, our Earth starts to form. And all of our humanity's history is completely compressed in just 3 minutes right before the new year. On December 31st, 11 o'clock at 57 is when human history starts in this calendar. So what happens after Big Bang? So as the universe, the Big Bang explodes, the universe or the space and time starts to inflate. It starts to expand very, very, very rapidly, and the universe at that time is super, super hot. So as the expansion is happening at a very high rate, the temperature of the universe starts to cool down, and because of that, atoms are able to form. And atoms, by atoms, I mean hydrogen and helium atoms, which are the smallest atoms that we can make. Um, and that part is what is shown here in the red or the pink colors that you see, and that's called the dark ages. It's called the dark ages because there isn't any object that can create light, and as galaxies are starting to form, which you can see as little blue specks around 400 million years from the Big Bang, is when the first stars and galaxies start to form. How do they form? The gas that is there in the hydrogen gas that is there in the universe start to condense upon itself due to gravity, and they start to become stars, and lots of stars together form galaxies and so on. And this goes on for another 13.7 billion years, and we get the wide variety of galaxies that we can observe today in our local universe, which are shown in the very right-hand side of the image. So I've been going on about galaxies, but what exactly is a galaxy is something that we also need to understand, because what we're trying to do is to understand when the first galaxies form. And to do that, we need to know what a galaxy is. So this image over here is a beautiful image of a spiral galaxy that is there in our local universe. So it is not that far back in time. And you can see the galaxy has these small sparkly particles. You can see that's kind of everywhere. That is the stars or the star clusters. There is this brown colors, like lanes of gas, or what we call dust. So dust is just larger molecules basically, and all of this gray stuff around is the gas that is there in the galaxy, and all of this is bound together by gravity and also dark matter. And dark matter does not produce any kind of light, so it cannot be seen. But we know that it exists by how the galaxy moves and so on. And we know that the galaxy actually is much more heavier than what it looks like, and all of that hidden matter is from the dark matter. So that is what a rough definition of what a galaxy is. So, and then how do galaxy forms? As we saw earlier, from Big Bang, when it was all completely just hydrogen and helium gas, they start to coalesce together within these places that we call nodes. And you can see in the second box, you can little stars or like little specks of sparkly things are forming. Those would be where the first stars and the first galaxies would form. And in the present day universe, you can see now the universe kind of looks like a weird web. We call this the large scale structure or the cosmic web. And all of our galaxies and stars live within this cosmic web. And like if you can see in the middle, there is like a high concentration of galaxies. That's what we call a galaxy cluster. And like these ribbony parts from the galaxy cluster we call filaments. And then there are galaxies that are living in little bubbles within the cosmic web, and we call them the void galaxies because they're alone in the cosmic web around there. So now to come back, okay. So, okay, I kind of said this already, but this is just a schematic of how the gas coalesce together, and we find stars in the gas together, which is the sparkly bits, and all of that, because this is a lot of gas is kind of coalescing together due to gravity. It starts to rotating, it gets a lot of angular momentum, and it starts rotating. And when you rotate something which is kind of loose, you start getting a disk, and that is how the disk galaxies are formed, or like any kind of structure in the galaxies is formed by this kind of rotation in the galaxy. And we saw that this is the beautiful image from a simulation called the Illustrious TNG cosmological simulation. And we see the cosmic web, which here the blue, everything in blue is actually the dark matter, which we cannot really see with our eyes or with telescopes. And all of the yellow things and the bright orange things are actually galaxies that are living inside the cosmic web. And within the galaxies that exist today, there is a very high variety of galaxies. They could be irregular or elliptical, depending on the shape of the galaxies. They could be spiral, when you see all of the spiral structures. It could be lenticular, or like a bar spiral, and so on. But so now that we know the kind of the history of the universe, or how galaxies come about, we can see that in the very early universe, galaxies are supposed to be very, very tiny, right? And this is a little video that shows again the Illustrious TNG cosmological simulation. We see how gas is actually coalescing together within gravity, and you can see little specks of stars or of galaxies forming over here, around there, on the top. And this is already within the first billion year of the universe that we are seeing. The tiny, tiny galaxies are starting to form. But they don't really look like the kind of galaxies that we expect today at the present day universe, which we showed earlier. As the galaxies start to grow and kind of merge together to form bigger and bigger galaxies, you see there is a bit more structure in the galaxies that come about. For example, here you can see there is a disk forming. It will be a bit more apparent in about few seconds. And there is more gas that is coming in, which is bringing in more galaxies. And you can already see this is a little disk over here, more galaxies, which are kind of looking like the kind of galaxies that we showed earlier. So it takes about first 2 billion years, first 2 to 3 billion years, for the galaxies that we looked that look like disks and spirals, for them to first appear. However, with JWST, so we really think before JWST was launched that all of the galaxies in the very first billion year of the universe should be very, very tiny, and there shouldn't be any kind of structure to these galaxies. However, with the launch of JWST, in the very first few months of studies, we saw not just one, but numerous of studies that claimed that there are galaxies that are as massive as our Milky Way in the present day universe. Now, this is kind of a problem for the model of universe that we have, because then galaxies as big as Milky Way, which formed in 13.8 billion years, has to form in just 1 billion year. And all of the astronomers and everybody in the community was very puzzled by this results. But it did make a lot, but it did catapult a lot of study to understand what these objects that this group had found really were. So there was a lot of confusion. This was one of the first results that were shown from JWST, which showed there was really, really massive, small, compact galaxies in the first billion year of the universe. So everybody was thinking, how can we form 13.8 billion years worth of star formation within just 1 billion year? Is our cosmological model in trouble? But good news was that it was not. So what really happened? So for that, to understand that, we need to understand how we study galaxies with JWST or similar with similar telescope. So when I said initially that you can think of JWST as a kind of a big camera. But the thing about cameras that is different about JWST is that JWST can split the light, like we saw in different Vibgyor colors, like the prism. It can split the light that is coming from the galaxies into different images, and we can get this kind of a spectrum, like a distribution of the light along the wavelength spectrum. And this we call the spectral energy distribution of a galaxy. So it's basically just the intensity of light of particular galaxy at different wavelengths. Okay. So now different galaxies have different kinds of spectral energy distribution, or what we call SED. I'm going to use SED a lot now. So you can see the first galaxy on the top right is the smallest galaxy in sample, and it's the shape of the SED over there is very, very different from the shape of the SED that is here, which is the most massive galaxy in this sample. The SED is much more flatter. Here, the SED is a bit more like a curve with uphill. The SED over there, again, in the right-hand side, it kind of cuts very fast. Here, there is a more of a gradual decline in the SED. So studying the modeling these SED is how we understand how much stars there are in the galaxy, how much dust there is in the galaxy, and also what kind of gases there in the galaxy as well. So this is how doing this kind of analysis is how initially the first results that were published, they said that the galaxy itself is extremely massive. All of the SED kind of had this kind of a shape where the galaxy looked like it had a lot of flux in this region, and the shape of the spectrum was not very sharp like in the first two galaxies. So here is the idea of what we call the Lyman break limit comes in. So when we are observing a galaxy, it's not just about how big and luminous this galaxy is, but also how far away from us it is. You can think of it as somebody holding a torchlight. If they are really close to you, it will look very, very luminous. But if they go really, really far away, the same torchlight will look very, very dim. So it's the same with galaxies. A galaxy that is really massive, if it is closer by, it will look really big and really massive. But if it is farther away, the same galaxy will look much more smaller. So, we need to understand how far this galaxy is to be able to completely understand what the SED shape of the galaxy should be and to decipher the properties of the galaxy. So one of the parts of the SED that we use to understand how far away this galaxy is called the Lyman break limit. It is simply the wavelength at which the light of the galaxy kind of drops really, really fast. That is because of all of the gas that is around the galaxy. It takes away, it basically absorbs all of that light over here, and you get this really sharp decline. So with the earlier result that we had seen, they had done a similar kind of analysis, and they had the images of those 6 galaxies in different wavelengths, and they see that these 2 wavelengths, which are in the shorter side of wavelengths, you don't really observe those galaxies. So here, this galaxy you can see up till here. But here, the galaxy completely vanishes. So that is why they thought that these galaxies are actually really, really farther away. And so that means something that is looking like this and is really, really farther away. That means it has to have a lot of the stars in them to be able to look this bright. However, later we did a little bit more studies. We had more observations, and these what we call the Lyman break galaxies turned out they're actually not that really, really far. It's because these galaxies are really not that big, and all of the the light that is coming from these galaxies is actually being absorbed by the dust inside these galaxies. And that is why this light is kind of dimmer. It's there. It's just that we are not looking for long enough to be able to detect that part in the images. But that was not all. There were other objects that were found later on that were genuinely actually really massive galaxies, and we had very good confirmation of those galaxies with the same technique, that these were in fact Lyman break galaxies. These were galaxies that are really, really farther away from us, and also really, really massive, but not as massive as initially thought, but still pretty massive enough for the first billion years of the universe. So, and we were finding more and more objects like this in the early universe. So what does that mean? So that clearly indicates that we were seeing something that was unexpected. So what does that mean for our model of how a galaxy is formed? You can see over here in the existing model of the universe, it takes about 1 billion years to even form a small clump in the galaxy. And so that means, and that does not work well with the observations that we were getting from the JWST. And that meant that we either need to make a lot of stars much more earlier than we first expected. So right now, our star formation is starting around 400 million years. Perhaps either our galaxies need to start forming much more earlier, or that the kind of stars that are there inside the galaxies, they have to be really, really massive kind of stars, which would make the galaxy look much more massive, or the efficiency of formation of stars from all of the gas that is falling in. As you can see, all of the gas is falling in and is forming this bright thing in the middle, which is the galaxy stars. So this formation of stars has to be really efficient to be able to form that bigger galaxy in the very first billion years of the universe. So just from a few images, we are able to tell that our existing model of how the galaxies are forming really need a little bit more of a tweaking, and we see more of this moving forward. Another unexpected result was in the very first billion years, we were starting to see structured disk-like galaxies in the universe. So this is one of the papers that is a bit more recent. This was published last month. And they find a galaxy that really looks like a disk. You can see the spiral arms a little bit going both ways. Maybe here, a little bit more evident. You can see there is spiral arms that is going in the galaxies. And this is when the universe is within 1 billion year of the year since Big Bang. And similarly, there were many other galaxies that were found, and we were finding that we were finding much more spiral or disk-like galaxies than we had initially expected before JWST. So a little bit of a recap once more. How do we get a structured or a disk-like galaxy? You need to have a lot of gas that is coming in, coalescing together, a lot of angular momentum that is required in the galaxy to form a disk galaxy. So this usually, before the launch of JWST, we used to think happens in about 3 billion years since Big Bang. But this result kind of bamboozled all of the astronomers, because we see a galaxy that looks very similar, a little bit similar to our Milky Way in the way that it is a spiral galaxy, and they call it Zhulong. And this Zhulong galaxy is formed within 1 billion years of the universe. It's very young to be in a spiral galaxy. Apart from Zhulong, we only have very few handful of galaxies that are spiral in the first 2 to 3 billion years of the Big Bang. So this is a kind of a big deal. And the thing is, our simulations, as we showed before, are not able to create this kind of massive spiral galaxy like Zhulong within the 1 billion years of the universe. So again, this shows us that astronomers need to build a slightly different model of the stuff of galaxy formation to be able to explain these kinds of results that we are seeing. One of the other unexpected results was the supermassive black holes at the center of the galaxies in the very early universe. So we saw that galaxies were already having these black holes which were active, and there was a lot of news about why are there black holes in the early universe, and again, we were trying to understand why this is happening and why we did not expect to see this many black holes, large black holes in the early universe. So we go back to understand what exactly is a black hole and why is this an unexpected result. Here I show a little schematic of what a black hole inside a supermassive black hole in the center of a galaxy looks like. It takes in a lot of gas and stars from around the galaxy within. It pulls it within itself, and then you can see there is this kind of steam-like thing happening, which is kind of how black hole throws away all of the things in that it is kind of pulling in. And almost all large galaxies in our local universe have a supermassive black hole at the center. Even our own Milky Way has a supermassive black hole, and you can technically see it in the Sagittarius constellation in the sky. So now, why is this black hole important? How does these black holes form? As I said, they take in a lot of the gas and star from the galaxy, and they grow in the size. So for them to grow in size, they need to be already in massive galaxies. And when they grow in size, these black holes, which is shown here in tiny little blue speck over there, but as they grow in size and they reach a certain limit, they start to blow out all of that stuff back into the universe around the galaxy, which is shown here as we call them outflows. And these outflows actually affect the evolution of the galaxies quite a bit. So this phenomena is of a lot of importance for us to understand how galaxies are forming and then evolving to become the galaxies that we see today. So again, the prerequisite for this kind of black holes to happen is that the galaxies need to be that much more massive so that they have the stuff to be fed into these black holes and then they can be active. Which is, again, not something that we were expecting, but we are seeing nonetheless. We have seen this wide variety of objects, which initially astronomers called little red dots. These are all, initially they were thought to be AGNs, or these supermassive black holes. But now with more studies, we are finding that perhaps a fraction of them are still supermassive black holes, but there are still perhaps some galaxies that are within that sample, which can just be small, compact galaxy and not necessarily black holes, supermassive black holes. But still, we are finding much more higher fraction of supermassive black holes than we were expecting. Now, these are all really unexpected results from JWST, and this opens up, all of these results opened up a large number of questions that still needs to be answered, and more studies from JWST and other simulations and other telescopes will be able, with those we will be able to finally answer the questions that were raised right now and to unveil how the galaxies are formed and how our Milky Way is also formed. And with that, I will stop and take any questions.
Okay. Okay, thank you, Anishya.
Mm-hmm.
So, you have any question from? Okay. Bomo zdaj malo slovensko, malo angliško. Lahko vprašate v slovenščini, bom jaz prevedel, lahko pa seveda Anishya direktno vprašate. So I just told them that they may ask in Slovene, but
Yeah, sure.
if they want, they can ask me. Okay, je kakšno vprašanje?
Te galaksije rdeče zaradi Dopplerjevega rdečega mejnika ali kaj?
Torej vprašanje je, če so te galaksije rdeče zaradi Dopplerjevega premika. So the question is if those galaxies are red because of the Doppler shift.
Not because of the Doppler shift, but because the blue part of the light from that galaxy is actually being absorbed by dust, which is why they look a bit more redder. Yeah.
Okay. Just checking. Also.
Absolutely.
Še kakšno vprašanje? Mogoče. I guess.
Perfect.
Okay, thank you, Anishya.
Yeah.
Lahko se zahvalimo zdaj Anishyi za podeljen praznik. Hvala tistim, ki ste prišli na Zoom. Na Zoomu bomo končali. Tisti, ki ste pa tukaj, vas pa Bojan prijazno vabi, da boste šli z njim. Danes sicer ni dobro vreme za opazovanje, ampak ko je Bojan rekel, boste malo postavili teleskop in bomo pokazali teleskope. Če še velja Bojan.
Ja. Koga zanima, gre. Tako z mano bomo postavili 2 teleskopa v televizionu. Že drži, kako.
Hvala.